By the way, you weren't live yet. I just clicked it, so now you are. I don't know if.
No, 2-1. Yeah, just push the. They gotta focus. Just push that one a little.
It's too. Needs to go in further. There we go. There we go.
Now he's gotta focus. Oops, zoom too far.
What's that? Because you're gonna be right here.
Okay. Is that focus? It's out of focus.
Well, I don't know how to focus it with your crazy.
Touch it. Touch it.
Oh.
I don't know why. Looks out of focus to me.
Sorry about the crappy apple quality.
Shit. Looks out of focus. You're supposed to like do the. Damn it.
Well, maybe if we back out a little bit. No, because you definitely want the screen.
Yeah, but look, we can, if we go back in, I
The
can,
camera just doesn't smoke.
that might be. I didn't clean it front of time. I didn't clean it for 2 days. Crap, it's gonna have to be.
Oh, darn. Oh, well. People are just going to have to put up with it if you want to see it live. That's all.
That's okay.
Can't get it to go live. We'll try. I think it's a differential between the lighting.
The light lit foreground. Yeah, we should at least focus.
It should. You're right.
Well, we're gonna get a high res more than capable anyway, so it doesn't matter. There you go. Yeah, when you get hit by the bus, the whole bus gets out. Oh! And the person in the car is like,
you guys ready? Ready?
Danny Terrio guy. It's on next. Danny Terrio?
Yeah, Danny Terrio. He's going to dance. He's going to dance. Danny Terrio's going to dance.
Okay, everyone, we're getting ready to start again. Okay. Read this narrative because I'm getting tired, so I can better read it. Okay.
that's what I get for being the last.
When we wrote our book about UFO statistics, during one of the interviews, I was asked my opinion about life on other planets. My answer was quite literally, I haven't a clue. And then I commented, I'm not that kind of researcher. Well, my friends, this is my pleasure to introduce you to that type of researcher. Here we have Mark D'Antonio.
Thank you very much. Yeah, I am an astronomer, and this is what we look like. I know that, you might think that's pretty odd. Usually you expect guys with big, thick, black glasses. Wait a minute. Well, the truth is that I knew I was going to be an astronomer at age 9. No lie, age 9. And all throughout my years, people kept saying, why don't you get a job where you'll make money? And I said, is that important? I want the answers. And my mother couldn't argue with that. And my father said, okay, but you know something? I did follow the dream, and I did become an astronomer because I believe that the answer for all humanity lies out there. You know, we're on the planet Earth, and the Earth itself is a temporary place. It's going to eventually go the way of the death of other planets we've seen out there. The sun is going to use up all its hydrogen. It's going to swell up into a gigantic ball called the red giant, and it's going to swallow our planet. Go home and pack. What are you waiting for? You only have 5 billion years. But as is in true form, and I'm sure Cheryl can attest to this, when you are actually talking about the human species, we tend to take our time and we don't see urgency until that last second. like the big red ball in the sky. You think we should go? You know? And the answer was, yeah, you should have gone 1,000 years earlier. Okay? So, you know, that's why we search for exoplanets. That's why we look for places where we can live that might not be anywhere near our solar system. In fact, they're most likely not going to be, because the sun's temporary too. So the question is, if we're looking, so might they be looking for their own reasons. And the question is, you know, we are just a single speck of dust in the universe, or as my idol as a kid once said, Carl Sagan, we are a pale blue dot. Right? Not bad, right? I mean, it's Carl Sagan, right? But, you know, and the fact is, you know, the question is, you know, have we been visited before by other species, okay? And, you know, could they find us? Well, we think we can find them. We're just looking for a particular type of chemistry in the atmosphere of a particular type of planet around a particular type of star. A lot of particulars. But there are so many stars that have planets out there that the particulars are actually quite you know, easy to overcome. Right? Statistics are on our side. And that's good news. Now, if we think about did anyone find us, you know, it's possible that it happened before. And it's also possible that, you know, we would find some evidence, but unfortunately, we don't really have any tangible evidence. Well, we have some. I mean, there's some circumstantial evidence, and the case I like to talk about is the case of the Wandjina in the Kimberley region of Australia. Who's heard of the Wandjina? Okay, and the Wandjina are really interesting because the Aboriginal people in this region of Australia said that the Wandjina came from the sky, lived under the water, and had complete mastery of the water. This is important because there is a Wandjina legend that discusses what happened when two boys, according to the Wandjina myth, tortured an owl. Well, you read it. And you know, what happened to them? Well, the Wandjina, in retribution, did that. They wiped out the village in a flood. And the Aboriginal village was destroyed. Now, could it have just been a tsunami? Yeah. Okay. But if you think about it, torturing an owl, for those of you that are familiar with the UFO arena, owls have a strange significance, don't they? Yeah, they do. So you ask, is it an owl or something else? Right? Okay. Now, I know the slide's a little ominous, but it's meant to be. Okay? Yeah, well, and the reason has everything to do with the fact that as human beings, especially human beings that don't have an advanced intellect, you know, at that point in their history, they don't have access to technology. Well, they might look at something like the gray on the right and think it's an owl. Right? Or an alien species might implant an image of a likeness that looks like an owl in the minds of the people that have experienced something. Yeah. We call those screen memories, or there's other terms for it as well. But, you know, I asked, you know, was it really an owl? Now, wait a minute, Mark. You're an astronomer. You're a science guy. Why are you talking about this stuff? You know, you should stick to your science. This is my science. Like it or not, here I am. Okay, and I think that it's important to understand that when we look at stuff like this, I have an open mind, and I have to think about all the things that go into such an observation, such a a comparison of a creature to an owl. And I say, you know what? It makes perfect sense to me. I think if there's an extraterrestrial species out there, there's no reason in the world that they can't be here. And I don't say, I want to believe, give me a tinfoil hat. I mean, I'm not like that. I believe from the basis of science. Much to the consternation of all the other people I know in the science world. Okay, I'm kind of an oddball because, well, you can see it obviously. Okay, they don't wear these color shirts. But the fact is, you know, we have legitimate reasons to think that maybe we've been found. Okay, and one of the things that we can do as a species is we can actually try to find other worlds like our own. And we do this because it's time to, for us to kind of rise up out of our little planet and move out of here. We're going to have to move. And some people in the short term say, let's go to Mars. Let's terraform. Sounds good until you actually look at the practicality of doing so. We have to be probably a full 1,000 years more advanced before we can do that. And by that time, we're going to already be interstellar. Mars will be a, what's that, a red thing? Yeah, it's a rusty planet. Let's keep going. We got to get out there, you know, and we'll be there. We'll have drives that are warp drives like the Alcubierre drive, created in 1994 by Miguel Alcubierre. And it's said that you basically can fold space. You subtract, you constrict the distance from your current position to your destination, and you lengthen the distance between you and your origin. Like folding the corners of paper together and stepping to point and not traversing the entire length of the paper. That's the Alcubierre drive in a nutshell, sort of, kind of. It'll work. But the fact is, it gets the point across that this is something we're heading for, and that technology is actually kind of already here in a sense, because NASA, through Sonny White, who's a physicist down at NASA, believes that the Alcubierre drive, for instance, the warp drive, is really just around the corner. Not only that, we've funded NASA, all of us, we've funded them to look at the warp drive. They have a funded lab. They're actually being paid to research it. And Sonny thinks, well, probably in about 30 years, we can have a small prototype that we can try and throw into a warp bubble. You have to create a warp bubble. It requires a lot of energy, so make it small, so you don't use much energy. To make a ship that can hold about 10 people, you need the energy of, you did before they worked on the calculations, you used to need the energy of the equivalent mass of the planet Jupiter, the largest planet in our solar system, all converted to energy to get that warp bubble. And you need to keep doing that to keep your energy. Very impractical, even for an advanced species, probably. So, they worked on the calculations and found out that they could reduce that requirement down to something the size of the Voyager spacecraft. That's a 10 to the 26 reduction, okay, 10 with 26 zeros, of reduction in energy requirement to actually make this warp bubble. And now it became practical. And Sonny White said, wait, what? And he began to work on it and got funding. So maybe in 30 years, we might have a small prototype. That would be cool. But right now, we're looking for other Earth-like worlds. And it'll probably take us about 30 years to find one just like ours. But then by then, we might actually have technology to kind of probe it and go there. That'd be cool. So what does Earth-like mean, as far as we know? Well, we need to have a planet that's actually in the habitable zone of the star. I'll explain. We need to have liquid water on the surface of that planet. I'll explain. And we need to have a stable star system. You know what I'm saying. Okay. So the habitable zone is this. It's that area around the star that's not too hot, not too cold, just right. And here's something new for you. Earth is not really in the best position. Our planet isn't as habitable as people think. It's always been that way. We just evolved into it. So for us, hey, a nice planet. I think I'll stay. Okay, but the fact is, we evolved into that, and it's not necessarily the best place for humans. We have to worry about tornadoes and earthquakes, volcanoes, Kilauea, you know. We have to worry about oceans and some of the factors the oceans cause on our climate. We have to worry about ultraviolet radiation giving us skin cancers all over the place. Who hasn't been to a dermatologist? Okay, you better all go, right? Because ultraviolet radiation is bad, obviously, and that's something that our star creates for us. It's something that it gives us the healthy dose of danger. And maybe the star is not as good for us as we used to think. And planets that are more habitable than ours are called superhabitable. That's a cool word, superhabitable. You say it like that, it sounds really important. Now, so far, we haven't found any superhabitable planets. We think we've got some ideas, for maybe some superhabitables that are out there. But these would also have to support liquid water, and liquid water is very essential for us. How do you know? Lick your forearm. Not now. But if you do, what do you taste? Thank you. Why? Ideas? Why do you taste salt? Well, yeah, but very good, you know.
Seawater.
Very good, and she knows the answer, and you know she knows the answer. And I like that about Cheryl. She's very smart. That's why Researcher of the Year deserved it. Very much so. Very good. So we're made of seawater, kind of like the similar salinity of the ocean. Do the math. Take your time. We came from the ocean. Exactly. That's why we're salty. We have a skin that carries within us a vestigial ocean that we walk around with like turtles. We carry it with us everywhere we go. Don't be dehydrated. Don't lose your ocean, or you'll dry up. Like fish in the salton sea. Okay? We will dry up. So, we can't do that. We have to have that salt. And that's because we are born from the water as a species. Does it mean that all species out there are? No, but the universe creates templates, in my view. This is something that is predicated on my observations of the universe. The universe has templates that are out there. There's a carbon template. I know, they call it carbon chauvinism. Yeah, that's the word for it. Okay, and they say, you're a carbon chauvinist. I say, okay. But there are carbon-based life forms. Look around you, you're one of them, okay? And the fact is, there's gonna be more of them out there. So why not look for them? Because we know what to look for. If there's a life form based on silicon, well, we're not sure what to look for. We're not even sure it's alive. What's alive? What's it mean? See? With carbon-based forms, we have more of a chance, you see, to figure this stuff out. So now, liquid water is very important, and that's always going to be a factor. And so we're going to continue looking for planets that have liquid water. We've found quite a few. Okay? Also, we need a stable environment for our star. Our star is actually reasonably stable, but not terribly. Who's heard of X-class flares? Okay, who remembers the great blackout back in, I forget when that was, because the lights were out. Yeah, okay, and there was a gigantic blackout that actually just like completely obliterated lights on the eastern seaboard. Why? Well, you see, we have a magnetic field around our planet, and high-powered solar energy spirals around those poles, okay? That's because the magnetic field keeps us from dying, okay? It helps us a little bit, not thoroughly, but some of that energy made its way into Quebec and blew out. In fact, it followed the basalt, which is lava rock in the ocean, in the rock strata of Quebec, and it followed its way right to power stations. That's the energy now from the sun. Spirals down, goes down to the transformers. We have an above-ground power grid. Yeah. Below ground would have been better. Shielded below ground, even better. We weren't thinking. What can I say? Tesla was right, So the fact is, we have an above-ground power grid. This above-ground, one more time, is that what it is? This above-ground grid is something that is really tough on us because the wires get induced magnetic fields and induced electrical charge when particles stream down from the sun, and they cause a major problem for us. And so it overloaded one tiny power station, there's the one in Quebec, and it blew out the whole eastern seaboard. And there's a guy, Frank, you think that's a problem? I don't know. And then whoosh, the whole thing goes out. All New England in the black. So yes, and that's because of our stable star. Thank you. So we need to have a stable star. Now, when we talk about stars, we want to say, well, wait a minute, what kinds of stars are there, and what kind can support life? Can all of them support life? Planets that can't support life, see, it's another thing. Can they support planets? Number one. And can those planets support life? Number two. And can that life evolve to something intelligent? Number three, that's way out here. Intelligence isn't necessarily a foregone conclusion. It's not a known destination. It's a potential path among many, and the planet speaks with a forked tongue, okay? You can go any which way at any time. Just look at our own history. the amount of extinctions that have happened on this planet. We've had 5 major extinction events, 3 of which were from giant asteroids. Okay? Now these extinction events reset the clock. Pow! And you know, those things took many years to actually have their final influence, their final say over what happened to life on this planet. And as you'll see when I pull something out of here later, which is going to show you how the Earth developed, then you're going to see a little bit differently, you know, how this affected us. So let's take a look at the stars real quick. Pretty colors. On the far left side of the screen, we have a giant blue stars. These are the O stars. And you'll notice along the bottom there's a scale, O, B, A, F, G, K, M. These are what we call the spectral classes. These are in order of highest temperature to lowest temperature. And it kind of relates to the biggest size, radius-wise, and mass, mass-wise, and the least mass, and the smallest radius, down at the other end. Things that are blue are hotter than things that are white, which are hotter than things that are yellow, which are hotter than things that are red. So it's these little stars at the far right end, the M stars. Remember Star Trek? It looks like an M-class planet, Captain. He meant M-class star. Don't correct Spock, you know. And so the M-class stars actually are the ones that actually have the biggest number of planets in our galaxy. And you can't see a single M-class star with your eye. And there's more out there than any other kind of star. Yeah, I know. And the reason that you can't is because they're so small in radius, their brightness, their intrinsic brightness, which is called luminosity, their intrinsic brightness is actually very, very low. And the nearest one to us, you can't even see with your eye until you use your telescope. I run the, it's on YouTube, it's called Sky Tour Livestream, which I encourage you to join. And on clear nights, we actually do deep sky forays. We look at these M stars, we look at stars, we looked at Tabby's star last year, which is the star that's been dimming over the years, and to show people what Tabby's star actually looks like. And we've seen a lot of different types of stars. We see clusters and galaxies and everything. And we do it in seconds, not minutes, because we're using a special camera, a special telescope in an observatory, okay? And it makes, it gives people a hands-on, one-on-one experience. And then we have a companion site on Facebook where people can go to look at the data we collected that night. And they can do all the things they want. They can do image processing if they like. Or they can just take the image processed images and say, ooh, I like this. And make it their background on their computer screen or something. But we do this because we love it, you know? And if we think the universe belongs to everybody, so everybody should go and enjoy it, all right? So these stars, right, in order of high temperature to low temperature, we looked at them all. We've seen them all. We found something when we looked at these stars and looked at planetary systems that might exist around some of these stars. We found that only stars from A down to M could actually have planets. These large O stars and large B stars typically don't have planets around them. They're too hot, they're too young, they have very powerful stellar winds, and they blow stuff out of their systems long before it can form planets. I kind of lied just now, and I'll tell you why. We did find a couple of B stars, you know, that had planets around them, but in fairness, they're what we call late type Bs, because one of the things I didn't tell you is within each of these categories of letter, we have a 0 through 9. So we have O, you know, 0 through O9. You know what? We've never found an O0 star or an O1. There's O2s and O2.5s and O8 and 9, etc. But we never found an O0. I don't even think we know what that is. Because those stars only live for a few million years. That's kind of bad. If you're a planet, look, I'm a happy little planet, and boom, you know, the star explodes in a supernova. There goes your fun. I know. And that's what it is, you know. So when we get to A, those stars last long enough so they can actually support planets for the long term. And the radiation, and ultraviolet radiation in particular, is not as bad as the O's and the B's. O's and B's, if a B star, late B, B8, B9, actually had planets, it'd probably be sterile from ultraviolet radiation. So anyway, these are the classes, and it really is A through M in our class list here. And there's plenty of stars like that, because luckily, the number of stars that are like A through M increase in frequency. The number of stars like the B into the O get very, very small, very, very quickly. So we don't have to worry about the O's and the B's because we can't have any planets around those. And that's what we're looking for, another home. You all recognize this from chemistry, and some of you are going, oh, not that. It's a periodic table of I'm crazy. Okay, the periodic table of the elements is important. I'll tell you why. Because everything you're made of, you heard this before, was once made in the heart of a star. Who did not know that? Be honest. I'm raising my hand. I didn't know that. No, it's true though. Okay, we actually are made of, as Sagan would say, we're made of star stuff. I mean, you know, he said that, but it's true. And to get the understanding of why, we have to look at how this works. I'm not going to go into the physics here. I just want to show you. The colors all represent how these elements are formed and where. Okay, we look at the yellow ones. The yellow ones are from massive stars that explode. The O's and the B's, and some of the A's. Okay, when those explode in a supernova, they create new elements, and they create all those ones you see in yellow. All right. Then we have dying low mass stars. Our sun's one of those, and those die in something called a red giant phase, and then it makes a planetary nebula, which is the outer shells of the star puff off and just drift away from the star. But those are made of elements, and those elements consist of everything you see in the green. All right. Now, a lot of times the stars are born with all these elements in their makeup, but they can't make these elements themselves. It's because this is what they were born with. Our sun has a lot of these elements in its atmosphere. We call it an atmosphere, the outer layers of the sun. But the fact is that sun could never make them. It's not hot enough in its core. The sun is hot enough to turn hydrogen into helium. Yep, we got that. And maybe in its later stages, maybe some helium into carbon. Maybe, okay? It's kind of on the border. So, but that's not the case that, you know, it doesn't mean that the sun is doomed to never, you know, create anything new, because once it creates this planetary nebula, this thing that comes out when the star puffs off its outer layers, those interact. Those outgoing layers interact with the interstellar medium, there's a word for you, the ISM, the interstellar medium, and they can create new things along the way. They can spur new star formation, and it's incredible. There's so much here, so much. That's a whole, you know, okay, it's like 10 years of study if you want, okay? But how about just no? We'll just move on. But you see, though, that the elements come from the stars, all right? And that's very important. Now, the question is, how do we find these planets? Well, clearly, the Kepler Space Telescope is one of those ways we did it. We still do, actually, because the Kepler was launched in March of 2009, and it was actually very successful. It looked at a little area of space the size of your fist extended in the summer sky directly over your head. That's in Cygnus, the swan, the constellation. And it looked at over 100,000 stars, as you'll see. Now, the sensor on the Kepler Space Telescope is curved like this. And for anyone who actually would like to understand why, it has to do with its accounting for something called the Petzval field curvature. What that means is that light of different colors focuses at different locations. All right? And so you have to curve the sensor to allow for that, all right? Because the lenses are typically, there's a convex lens. Okay, well, the light coming through here is going to focus differently on the sensor than light coming through the center. And this accounts for that. Okay? That's why it's curved. Now, the Kepler consisted of everything you see here, but most importantly, I want you to see the reaction wheels. And what are those? Well, they're actually like, think of them as little circular masses that are mounted on the telescope. There's 4 of them, okay? Kepler had 4. And they look like this. You can see them here on the left side a little bit. They're called the reaction wheels there, right? You see it here, one there, and there's another one here, another one there. And there's 4. What are they for? See the angle they're on? Well, they spin. And when they spin, they impart a torque. And they make the telescope turn in a very specific way, like I just did, okay? And it stays there. So now that's how they turn it, without using rockets, like, you know, because it would simply run out of fuel very quickly. And the Kepler, you see, has solar panels, which charge the machine to actually spin the wheels. And that's very good. And here's a close-up. I actually took this photo. This was, I was working on a satellite project in Phoenix. And I was in charge of building very high-end models of their satellite, very high-end engineering models. And to do that, I had to understand what was going on, because I had to understand where everything gets routed and everything. And so you have to understand that these are done in clean room conditions. The building this was in, and I'll tell you what satellite was in a minute. The building this was in was 2 or 3 stories tall, and there were 25 people in there at any one time. And every person in there was dressed like this, okay? And yes, that's me, different glasses, okay? This was taken by a guy named Jim. But the reason I show you this is, do you see that black cord, the spirally cord? Okay, that has a little alligator clip on the bottom. And when you got anywhere near that satellite, you had to clip that onto a very important metal rail. And it drained all the electricity off your body.
Grounding rail?
It's a grounding rail, exactly right. If you didn't do that, you stood a chance of taking this $340 million satellite and reducing it to electrical pulp. Okay, because you had a lot of charge in your body, and the smallest static charge could find its way into a circuit and sit there for a year until it got to orbit. And you went to turn on that circuit, all of a sudden, oh, what happened? You see Frank running away as fast as he could. Don't blame me. You know, and that's the thing. Okay, so I was actually on this particular day. I was in, we call it the high bay. I was in the high bay, and again, I was just a contractor. Okay, and as I was watching them, you know, do some stuff, I saw this one guy walk, and the rule was 3 feet. You get on the rail from 3 feet out, 3 feet close, right? I watched the guy walk around something that was on the ground right here. And the satellite was there. He just went around this object and then back away. He was fired on the spot. I watched it happen. I was like, wow. Make sure I'm plugged in. I'll plug in 25 feet away. You know, I'm still plugged in. I'm plugged in. You know, and I was taking photographs, all right, of this satellite. Now, the thing to understand is that going in and getting suited up like this is extremely comprehensive. It took me an hour and a half to get to this spot. And the reason was, the first thing you do is you put your feet, your street shoes, into this little unit. It clamps your foot and then yanks and sucks the junk off your foot. It feels like your foot's being pulled off your body. What's happening? Just bear with it. Okay. And then you have to do it again. And it's really, and you feel it like a vacuum cleaner from HE double toothpicks. I say that because I can't say hell. Oh, you know. And it's really powerful. And then you put booties over that, and then surgical garb over those feet, and booties over that again. Why did you just do that in the first place? Why do you have my foot pulled off? You know, and then you do the same with your hands. Okay, okay, and your face. You notice I'm out in the open. Yeah, I didn't get anything. They didn't touch my glasses or anything. And my camera, which was out there photographing everything, you know, they didn't really. I don't know. They weren't thinking. They let my camera in. I saw street dirt on it. I said to the guy, "Hey Jim, I got dust on here. Is that a problem?" I think it'll be okay. Okay. But they fired a guy for being within 3 feet. You know, it wasn't quite right. So we're getting better. Okay, we're getting better. Trust me. So, but the point is, this kind of garb is not optional because the things that can go wrong on orbit can and did. With Kepler, okay, 4 reaction wheels. It needed 3 to operate. It lost 2. So now it can only go, oh, I can't look that way anymore. And now it's stuck going this way when you really wanted to go back there. And that was the end of Kepler. Until a bright engineer decided, well, the sun has a force that it imparts on the spacecraft with its solar wind. And that force actually can be used to our advantage. So what they did was they actually used the force of the sun hitting the Kepler Space Telescope as a reaction wheel. And they reprogrammed the other 2 that still worked, and they made it so that it could be repointed. And that rejuvenated and restored our Kepler Space Telescope. Ta-da! Yeah, it's great. And they called that the K2 mission. And it's still active today, as you'll see. I'll show you. So, overcoming, you know, a foible of ours, and something where we actually destroyed a thing inadvertently like this, can be corrected, but man, they were lucky, you know, because it would have been the end. And since then, another 1,200 candidates were discovered by the K2 mission plus more. There's a total of 4,000, okay? But 1,200 very likely, bless you. I know that was tough, so I sneezed, brain. And so there was, you know, that was actually very tough for us to figure that out. I didn't figure it out, but it was tough for engineers to figure that out. But, you know, in the end, we did it, and, you know, Kepler's working again. What's it doing? It's searching for transits. What are transits? Well, that's when the planet that might be circling the star passes between us and the star, as seen from here. We see a little tiny drop in the star's light, and that's represented by that curve at the bottom. That's called the light curve, right? And so the light looks good, and then as the planet gets on there, as it starts to move onto the star, you see it drop a little bit, and then it maxes out at the bottom, and then it starts coming up again when it reaches the edge. Now, you see those parts that are sloping right there at the edges? When the James Webb Telescope goes up next year, the James Webb is going to be able to look at those slopes and figure out what's in the atmosphere of these planets. Wow. That's important, because to this point we can't really do that. The Hubble can see under certain special circumstances, you know, what's in an exoplanet's atmosphere. I mean, it found helium, you know, so just recently, so we can all talk funny if we want to. Okay, you found helium. Great, that's good news. No, that's good news. But we need to actually do better than that, and the Webb is going to be able to look at these constituents in this atmosphere and figure out, do we see oxygen? Now see, here on Earth, you see, we have oxygen in our atmosphere. You can do that. But did you know that it's not supposed to be there? Did you know that our planet is in what we call disequilibrium? The oxygen loves to bond with materials that are in the crust. Let's jump over to Mars. Mars has a lot of iron-rich compounds and minerals in its soil. And the oxygen that used to be in the Martian atmosphere, and it was a lot, all right? That oxygen has gone into the soils, and Mars essentially rusted. That's why it's the red planet. Ta-da, you know? And it's iron oxide, you know, FeO2. Fe is the iron in the periodic table. Remember the periodic table? And then FeO2 is the actual stable compound. And that's rust, iron oxide. And so that's happening all the time here. But see, on our planet, oxygen's being replenished. That replenishment mechanism is life. So when we look at an exoplanet elsewhere, we're looking for this replenishment of oxygen in its atmosphere. And that's what the Webb's going to find. And when it does, we will have found another planet that most likely has life on it. Yes, oxygen can be produced by other means, but not in the amounts like we see in our atmosphere. Okay? Who knows the primary producer of oxygen on our planet? Yes, that's a generic answer. Specifically, that's the process, correct. But what's the specific thing? Yeah.
Blue-green algae?
You got it. Plankton. You thought plants, thinking, oh, green plants, like I grow in my study, I got little plants that fall over. Yeah, actually, to be honest, plankton slightly edge out plants by, you know, regular plants, land plants, by a little bit. But you were close, because you wouldn't be wrong, actually, to say plants. But blue-green algae are plants, in a sense. They're just in the ocean. And it was blue-green algae that actually created our oxygen atmosphere and ate carbon dioxide, little carbon dioxide gobblers. So, how's it feel to be breathing bacteria poop? Because you are, okay? But it's all right. Yeah, we feel good, don't we? Yeah, exactly so. Yeah, I know, okay. But that's the thing. See, so when our planet developed over time, this is exactly what we saw happening, okay? We saw this rise in oxygen, this the lowering of carbon dioxide. But guess what? I have an application that actually shows the level of carbon dioxide in our atmosphere over the last 1,000,000+ years. And it's doing this. It's not this. And then as it gets to us here, we're going up and up, and it's not that at all. It's this. There's no really high peak coming or going. It's this. So when people say, we're causing climate change, guess what? I mean, as a science guy, I say, I understand that. Certainly we have a contribution. But look at the real data. I mean, from the real data, you can't tell it's us. Okay? We need more data. Another 1,000 years will tell us the answer. I'm not saying that we're not doing it. I'm telling you that it's doing this. In fact, it was a lot higher before. In fact, that before means well before we ever existed. Okay? Lucy wasn't even, Australopithecus afarensis was never even a concept at the time. And carbon dioxide was up in the, several hundred parts per billion. And now it's a lot lower. It's like 200 and something. And that's because of a lot of changes that happen here on the planet. The planet goes through cycles. I'm not saying we're not contributing. I'm just saying that the real science is showing us that it's been fluctuating for millions of years. So we don't have enough data to say it's us. So I mean, that's just truth. I'm sorry, And I know that we should be stewards of the planet, and we're going to continue to be stewards of the planet, and I'm all for it. But I don't want to see us blamed for something that we don't even have the data to prove yet. But we can prevent it, sure. I'm all for preventing it. I love alternate energy sources. I designed Gulf Stream windmills. It would sit under the Gulf Stream, and the vanes were made of fabric, right? And these things would spin very, very slowly. So slowly that, in fact, if they hit a whale that was going through, they would just fold around it, unfold, and keep going. Okay? It was sort of like a slow motion thing. Even a submarine could go through them and just like hit them. What's that? Well, I think I just hit another windmill. And basically, they would keep going. And it would generate power very slowly. I mean, wave action, it never stops. Let's use it, Solar power, excellent. But the efficiency of the panels, not there yet, I documented in my book, The Populated Universe, and which will be out hopefully in a few months. I keep saying that, but I keep having to edit and edit and edit. But I finally have an editor now, thank you. So, it took time. You never edit your own stuff. Never. You'll never finish. Okay, so transits are what we look for with Kepler. Now, here's what I told you before. A fist-size area at arm's length in the constellation of Cygnus, this is about August. You go outside at August around 8:30, go like that and say, wow, that's all that we found. That's where we looked with Kepler. And that's where we found many of these candidates, these planets, exoplanets. This is all good. And it's just a statistical sampling. You extrapolate that to the full number of stars we have in the universe, okay? And we're talking possibly of, we've got 2,000 planets plus. This has actually, been upgraded to 3,600 plus another several thousand candidates. It's going to go on and on. We're going to get to the point where we're just going to say, let's just stop counting these things. There's so many. Let's just look for ones like us. And that's why you hear science saying a lot. I think that there's probably more planets than stars in the universe. And that's a true fact. There are. You remember when people thought that we were the only planets in the whole universe? Myopic. Silly. And it's not true. We're not. So we look there, and the thing is, there's other methods to find these planets. And we use something called, this is radial velocity, where if something's coming towards you, the light from it is actually shifted toward the blue. It's Doppler effect, yeah. And as it goes away, it's shifted to the red. In sound, you know that very well with sound. Okay, a train comes by, or a car beeping at you to get out of the road. Okay, that's the exact same thing. So that shift of frequency happens with light as well. But you don't hear sound, you see the light change color. Blue toward us, blue shift, red away from us, red shift. So by studying that redshift, we can actually figure whether a star is moving, and if it is, how big the thing around it that might be causing it to move has to be at a low end. We can actually kind of figure that. This is used as a confirmation to a transit to make sure it's not a thing that, like a star spot, like we have sunspots. I mean, a sunspot could look like a dimming of a star because it's an area of the sun where there's a geomagnetic storm, and as the sun rotates, that star spot comes around, that sunspot goes around, and as we see, the light from the star might diminish a little bit and look like that light curve we saw before. Well, this is how we confirm, because you won't get a shift like this with something that's actually not, being subjected to something else's gravity pulling on it, which would be a planet. Okay. So then we have direct methods. A direct method, sorry, I didn't mean to be in your way. A direct method like this one we used infrared radiation, being detected from this planetary system, and we saw this is the first photo of a full planetary system. And I talked to Peter Michaud at Mauna Kea. This is the discovery image for the Gemini telescope at Mauna Kea. And this was a wonderful program still going on to find exoplanets, planets around other stars, that are visible by ground observation. That black disk is not a black hole. That black disk is called an occulting disk. It's an artificial blocker to the star's glare. Because if the star was allowed to glare and see the brightness of the actual star, then that star image would be bigger than the entire screen, just the glow of the star. You occult it and get rid of it, and now look what you can see. You can see the planetary bodies orbiting it. That closest circle down there at the bottom is as far away from that star as Neptune is from us.
Wow.
So you can see how big this system is. And what's inside the disk? Probably more planets. We'd have to study this to see. See, so there's other methods like this one, this direct imaging. And this one's called astrometry. This is where we actually measure the position of a star over the course of several years. This position here that you see here, this is our own sun, okay? And if you look, there's a yellow dash right there, a yellow dash circle there that you can see. That's the diameter of our sun. And that wobble that you see is the wobble, that path of the sun that it takes because of the influence of all the planets around it. Very complicated. And some of those movements are actually inside the sun itself. In other words, it moves like this. It doesn't move way out here. It moves like within its own self. Okay? And we track that. And this is what comes up. Notice those little numbers you can't read, and I can barely read from here, are years apart. See? So that's how long it takes. So there's a lot of different methods to find these things. Now, another method, which is kind of fun, is this. It's called gravitational lensing. And this is something that I can't remember. The other day I ran up against someone who simply refused to believe it was even possible. But, I can understand. Not many people realize that light is also subject to gravity. Wait, light? Light has mass? Well, no. Wait, it's subject to gravity? Yes. So it has mass? No. Welcome to my world. Okay? Yes, it has relativistic mass. What's that? Have you taken a general relativity class? No. So, but in other words, there's a gulf of knowledge sometimes when you're trying to impart this to someone. However, I can say it this way. Small photon packets of light will react to gravity. And they do because we see it happen. So whether you understand how that happens or not doesn't matter. It does happen. We watch it. During eclipses, we can see it happen around the sun. So we know it happens, so this is important. So what's it mean? If you have a star going out there in space somewhere with a planet going around it, and then you have a star way out here that happens to line up near the planet as it's going around, then as the planet comes around and goes near the image, the star that's way back here, that star's image gets warped all of a sudden. You see the star suddenly, instead of being like a second point of light near this other star, it suddenly becomes like a ring. Whoa, that's weird. Well, that ring is actually an effect of gravity, and we call that a gravitational lens. There's many photos of them out there. You can actually see a gravitational lens online if you look it up. It's really cool. So that said, so gravitational lens is another methodology that is used. Now, if you're interested in exoplanets, there's an exoplanet catalog. You can go ahead, it's called the Open Exoplanet Catalog. It's online. Or if you have an iPhone, you can download Hanno Rain's application called Exoplanet. And I have this application. I've talked to Hanno a few times. Great guy. He takes and puts all the latest and greatest exoplanets in here as the news comes out. You see it and you hear it, and you can go view these. You've got so many parameters if you're interested. Now, this is the K2. Remember I told you Kepler rejuvenated? This is the K2 database now. As of July of 2015, everything in blue, okay, is something that came in from as of January of 2015. And then the yellows are as of July 2015. So you see, not even quite a full year, and we already see there's a lot more candidates. There's a lot of dots. Thank you, K2. So, and it's just going up and up. Now, the Spitzer Space Telescope is an infrared telescope. It has a mirror that's only 2.9 feet in diameter. Okay? 2.9 feet, you know, it's not even 3 feet. Okay, the Hubble Space Telescope has a mirror that's 8 feet in diameter. Okay, and we use this to actually explore exoplanet atmospheres right now. It's hopelessly, you know, outclassed by the Webb when it goes up, but the Webb ain't up there yet. So there's the Webb. Looks odd, but the Webb has a 21-foot mirror compared to the Hubble's 8-foot mirror, and to the Spitzer's 2.9-foot mirror. Okay, it's a baby telescope compared to an adult telescope. Okay, this is what they look like when they grow up. Okay, and faceted mirrors like this, when you see these mirrors that have all these, you know, segmented mirrors like this, we couldn't do this before, but we can now. And the fact is, this goes into space, and then these all unfold, and they form this flower petal arrangement. Then they adjust them and they calibrate them, and that's what you get. So now, as we go down, we see, you know, this 21-foot mirror really handles a lot more than that 2.8-foot mirror of the Spitzer, and it's far better at looking in the infrared. So we have conclusions. We have current estimates that vary, but we think that there's, you know, this is the result. We think that there might be from as little as 25 million Earth-like planets in our galaxy alone,
Wow.
up to you know, 10 to 20 billion Earth-sized planets that are habitable in our galaxy. That's an important finding. It's a very important finding. Now, we're only getting started. It's only going to get better, you know. So, what does it mean for a planet to develop life in the universe? You know, I said this many times, but we only know one that has, okay, and that's ours. But to understand how life developed, or how it could develop elsewhere, we have to look at how it developed here. And as my last thing to do with you tonight, because I'm sure it's probably getting warm because they probably turned off the air conditioning, okay? So now we're all melting, okay? To do that, I have something that will help us, and that is a very special high-tech piece of apparatus to roll toilet paper. That's right. That's right, I'm bad. This is a roll of toilet paper, okay? Held together by Velcro. And Bill's Skywatcher's gonna help me, and Eric's gonna help me. Thank you. So, I don't know how this is gonna work because this, wait. Susan knows what I'm doing. Because I did this in Leominster, Massachusetts. I actually had to use it like this. And it was really kind of odd, but it worked. So we're gonna do it this way, one more time. On this roll of toilet paper, which is rather customized, I actually created the history of Earth. From the very time it formed to us here in this room. Just for you. It's not used. But I'm going to show you how this all works, and I'm going to kind of, we don't care what's up there, but you know what, let's go out front.
There we go.
All right, right here. No one's in the way. So I'll just hand this to you for a minute, and now I'll go like this. So here we see, this is the formation of the Earth. This is, by the way, for those counting, sheet 298. Okay. This is at location 117 feet. That's how much is left, okay? Here you go, Bill. So take that. And I'm going to come around this side, and I'll be out here. No, I'm kidding. So what we see here is the formation of the moon. Okay, this happened at sheet 291. Okay, and that was literally 4.5 billion years ago. All right, if you may. Oh, the oldest recorded Earth rocks are here at 4.4 billion years ago. Okay,
Wow.
This is sheet 284, and each sheet is around 4.3 or 4.4 million years. So. Yeah, you got it. I forgot my spindle. I'm sorry I forgot it. And now, thank you, Bill. Here we go. And now, remember your cyanobacteria you mentioned? The blue-green algae, right? Here they are. Okay. Updated predictions are that the atmosphere began to form around 4.2 billion years ago. Shortly after that, and after the oceans began to form, we had the blue-green algae, and you'll see them shortly. Shortly, room time, not Earth time. So if we keep going, okay, keep going. Yeah, I know it's gonna keep going.
Are we like passing in millions of years or?
Billions.
Billions.
Yeah, well, actually millions are right there because it's 4.4 million a piece or so. Actually 14 million years a sheet. Yeah, okay, there we go. Okay, here you go. I know it took a while. You can count the years. but don't wait for it. Because this was literally, this is sheet now 220, and this was way back then around 3 point, notice I don't have an age here, because it's varying. People are saying 3.8 billion years ago, 3.2 billion years ago, whatever. It happened over 3 billion years ago is when the blue-green algae began to come alive and be able to form enough to start creating oxygen in our atmosphere. Everything that happened in between here was when the oceans formed, okay? So, you may now go and see what happens. Don't worry about it. We're going to go. Oh, he dropped the earth. He dropped the earth. The entire planet just shook. It's all right. And we keep going. Yeah, it's the end times for Bill New York Skywatcher. So, as we keep going, you'll notice a lot of nothing is happening. Yeah, well, not really, because what's going on right now is those blue-green algae are percolating, and they're actually creating an oxygen atmosphere and eating the carbon dioxide. Oh,
There we go.
alert. Right. So now we get to sheet 174. Okay, and this was 2.7 billion years ago.
Wow.
Remember how far back we went? 3.2 to 3.8, right? And this says the buildup of the oxygen atmosphere. Ta-da. Not to these levels. No way. Actually, it was more. We had a lot higher oxygen on this planet. We had dragonflies this big.
Wow.
That was a big dragonfly. Where are you going to take my pet dragonfly for a fly? I mean, that's a big creature, you know? So that happened right there, 174. Keep going, that's 2.7 billion years ago. Right? Now you see that we're getting down pretty much here a little bit. Hang on. Oop. Ow. All right, now here we have the beginning of what we call the Archean times. And this is the Proterozoic era. About 2.5 billion years ago, the earliest life forms start to show up. Okay? So, someone keep going? Yeah, be careful, Billy. We got life here. Okay, that's it. Keep going. Again, looks like a whole lot of nothing going on. Sounds like a song. Okay, but as we go, all right, you see still things are happening. The earliest life forms, so they're percolating this whole time. Millions upon years. 14. It added up. It keeps going. It takes a long time. Luckily, we have toilet paper. Can you imagine if we didn't? Oh! Well, this isn't life. This is the formation of the earliest supercontinent called Rodinia. Okay, and this was 1.4 billion years ago. See, we're still in the billions.
Wow.
You know? I can take this out now because these guys are helping me. All right, let's keep going. And wait, that's sheet 90.
Getting there.
Yeah, we're getting there. These are 4 inches apiece, so you can do the mental calculation. All right. Aha. These are the first known animals 1.2 billion years ago. Let's keep going. See the difference in time there? That's millions of years past there between those and those. Thanks for doing this, Bill. I appreciate it. Eric's got the hard job.
Yeah, it's real.
All right, so now at this point, this is sheet 87. I'm sorry, sheet my little writing, sheet 51. Okay, I just changed the history of our planet. Okay, but now we're at 800 million years ago. Finally, we're in the millions. Thank you. We're almost home. Not really, but that happened like there, and that's 800 million years ago. Okay, and that's when the first supercontinent began to break apart. That means plate tectonics started to come into force and started working its little magic. All right, and that's why the early supercontinent, all right, broke apart. All right, keep going. What? You see, you gotta breathe now.
We're getting close.
You might want to roll a little more. Yeah, and this is sheet 45. This is actually the early multicellular organisms. This was 700 million years ago. All right, not even to the Cambrian era. Remember that? Okay, that was like the earliest one we always thought. The Cambrian era, that's ancient history. Watch. Okay, keep going, please. So now we keep going here. Keep going. Oh, wait a minute. Things are starting to happen. What's going on? Okay, let's just go a little more. Poor Bill. Sheet 35. Early shelled organisms occurred right here, okay? And guess what? This is the pre-Cambrian era. And yeah, we're not in the Cambrian yet. Don't even think we're in the Cambrian. Okay, we're not even there, but we're getting there. And this is about 544 million years ago. Okay, great. And by the way, all along the way here, we've had extinction events occurring. And I can point them out as we get closer. I have a few. So the Cambrian era begins around this sheet, 34. Okay, so about 500 billion years ago. 500 million years ago. And then the Cambrian era ends 510 million years ago, and we get the Ordovician era. Yeah, we have all these era names. You know, go figure. You know, we like to name things. Okay, keep going. Thanks. And now, on sheet 31, early fish, 490 million years ago. That's when fish happened. At least started to. Okay. Now, as we keep going a little bit, okay, on sheet 29, 450 million years ago, we had early land plants. Okay, think that through. Early land plants. This is when the transition to land occurred. Okay, about 450 million years ago. That's when this actually occurred. Oh, I'm sorry, 440 million years ago or so, just around this. That's when the transition to land plants began. So the animal kingdom hadn't even conquered the land yet. This was all ocean. Not all ocean, but we had a lot of land mass. But only here did it start to move onto the land, which is really cool. All right? And then we start the Silurian era here, 440 million years ago. And we keep going, and the Silurian comes to an end 408 million years ago, and we get the Devonian era. What's that? Well, the first major insects occurred here. And we have these 400 million years ago. And now, you know, dragonflies the size of a car or whatever, you know, carry you away, you know. Not that big, you know, I'm exaggerating on that. But then we had about 340 million years ago, we have the first reptiles. Okay, 340 million years ago. Look how much went by already. You know, this is important, keep that in mind. You can't help to, I mean, it's right there. Normally, if we had the room, what I do is I actually walk around the room. You know, I did this in Arkansas, and it was like 800 people. And I literally wrapped them in this thing as I walked around. And the guys running the video were going, "Are you nuts? I can't follow you." They did. They did. You know, it's what happens. So then here on sheet 18, this is when Pangea was fully formed. Not when it broke up, it's when it was fully formed. 18. This is 280 million years ago. Sheet 18. Remember we had like almost 300 sheets. Okay. All right. And look at this. Something you might be familiar with, the Triassic begins. This is around 245 million years ago, and the Triassic ends 208 million years ago, and the Jurassic begins. That's when Jeff Goldblum became a scientist and started talking about Jurassic. You don't believe me? You know? Well, anyway, so we keep moving, and now we see on sheet 12, literally just after the Jurassic begins, guess what? The Atlantic Ocean opened up. That's when the Atlantic happened. Ooh, that's cool, right? And then we had early birds and mammals 180 million years ago. Wow, okay? And this is on sheet 11, okay? 298 sheets. So then we have early flowering plants 150 million years ago. That's when flowering plants formed. Now that was an evolutionary mutation followed by an adaptation, okay? Mutation and adaptation, that's what happened here. So that mutation took advantage of the fact that some creatures, these insects that you saw before, learned how to pollinate. Okay? Pollination became a mechanism to transfer, okay, material and to continue the species. That was a mutation taken advantage of by the planet automatically because that worked to continue the species. So that happened 150 million years ago. And then I have to now take this off because, you know, this is where we are today, okay? And if you look here, actually, can I get you to hold it for me? Thanks, Eric, I'm sorry. So right here we have the Rocky Mountains formed 80 million years ago, and that's that far, okay? And then we have the Jurassic Park, yeah. Dun, da, da, da. The Jurassic era ends here 65 million years ago with a major extinction. This was called the Cretaceous Paleogene boundary. It's what we call it because it used to be called the KT extinction event. It's Cretaceous Paleogene. It's just the era, the names to confuse you further. So when you get the first way, we'll just throw another way at you, you know, because we're good that way. Okay, and this is when people say, well, this is when dinosaurs were, you know, rendered extinct. Extinction took a long time. Dinosaurs just changed. The oxygen levels were dropping the whole way, so animals were getting smaller anyway, The asteroid hastened that by putting a lot of particles into the atmosphere, which caused what we call nuclear winter now, we understand. But it made this so that the animals that were meat eaters, they would eat the plant eaters, and the plant eaters would eat the plants. But the plants were dying over several years because there was no light getting down. It was very, very diminished because of this large pall of dust thrown up worldwide by this asteroid. Okay? We even know where that asteroid came from, by the way, and I'll tell you. Just remind me if I forget. So they were rendered extinct over a period of a number of years, maybe probably about 500 to 1,000 years is when it really started to wane. And this problem actually, it didn't stop the Earth from evolving, it kept right on going. Because here on sheet 3, well, this is where India collided with Asia. Yeah, you ever see the Himalayan mountains? Boom! Made by the collision, slow motion, with India and the Eurasian continent. Okay? Continental plates are really interesting when you look at them, you study these tectonics. It's just crazy stuff. To be an astronomer, you have to know something about planetary science. It kind of goes with the territory. So, when I see a volcano erupt, I go, yeah, I want to go there. Everybody else says, you're a nut. I go, yeah. I want to go to Kilauea. And I put my foot in the lava. No, I don't want to. Never do that. But, so yeah, this is where, this is sheet 3. This is where, 3. This is where the collision of India with the Eurasian continent happened. Okay, making the Himalayan mountains. And by the way, also here is where global cooling begins, as we entered an ice age at this point. Okay, and this was 40 million years ago. Now, we come a little farther forward now to sheet 2, and that's 23 million years ago, and it's the beginning of the Cretaceous era from the Paleogene era, all right? And this is the point where we actually had the first ice at our poles. It's the first time we had ice in the Antarctic and the Arctic. Isn't that amazing? Kind of that's a finger's way. It's a recent event, doesn't it? See? And thank you for this, by the way. And the first Antarctic ice happened up here, okay, about 10 million years ago, or about 12 million years ago. And then right after that, the Red Sea opens up around 10 million years ago. And this little tiny line right here, okay, that's Lucy, 4.4 million years ago. I mentioned the Australopithecus afarensis. That was the first precursor hominid, bipedal being, to us. That we think, and there's a lot of competing theories. But that's where Lucy is, right there, about 1/4 inch from here with us. So what does this all tell you? This is your history of the Earth. This is the kind of thing that would happen anywhere else in the universe. It probably would take this long. But see, stars are long-lived, and in general, they're very stable. And this kind of thing can just happen over and over and over again. See? And this is my homage to the history of this planet. Roll of toilet paper. I know it doesn't sound too exciting, but it is something that really gets the point across. Because what I want you to understand is, if you look here at the beginning, okay, and you look here, where dinosaurs were rendered extinct, and you compare this distance to how far down this would go, another 100 and something feet, it shows you the truth, and that is that dinosaurs are recent history. They just happened yesterday, as far as the planet's concerned. See? So it gives you a new perspective on life on this planet. Also notice how we saw a lot of nothing for a long time, but then when we started seeing life, it accelerated and exponentially increased, and boom, at the end, it just went bigger and bigger and bigger. And throughout multiple major extinctions that happened on this planet, life continues. And I know that, and I go back to Jurassic Park because I kind of like that movie. Right? Yeah, Jeff Goldblum as Ian Malcolm, the scientist, says, life will find a way. Okay? And, they said, no, well, yeah, life does find a way, and here's the proof. So there you are, the history of the Earth on a roll of toilet paper. I want to thank you guys. You've been wonderful, and I kind of went about a few minutes over, maybe 5 minutes over, I think, based on the length. But, did you like this? Was it good? Yeah. Awesome. Thank you. If you have any questions, I'm not available. If you have any questions, I'd be happy to answer any, if you have them. If not, I might have talked too much, and I'm okay. Yeah.
Where'd that satellite come from that? Did they say something?
Oh yeah, thank you for reminding me. And I'm gonna tell you about the satellite that I worked on through that model. I said I was gonna tell you where that came from. The asteroid that caused the extinction event, we have actually we've traced back to the inner asteroid belt close to us. And it's a member of a certain family of asteroids. We've named asteroids a certain family of asteroids that are based on their composition and their movement. We have the Trojans. Okay, we have the Apollo asteroids here around near the Earth. But these asteroids at the inner edge that look to be the ones that were easily dislodged that came here to do this are ones called the Florians. F-L-O-R-I-A-N, the Florian asteroids. And we think that it was one of the Florians that got us. And it was only about 10 kilometers across. You know, it wasn't very big, but it was enough to. You got to remember, impact energy is kind of important. You know, if it just sort of floated to the Earth lazily and started, from zero, in space and just fell to the Earth, it would not have caused nearly any damage like it did. It hit us probably several thousand kilometers per second. Coming from the outer, the asteroid field and coming in sun's pole. It just was on a total collision course with the Earth and whacked us good. So,
Mark, could we detect something like that now?
what's that?
Could we detect something like that now?
Not yet, but I have more to this presentation, but I'm not going to do it in the interest of time. But we're actually creating a system to track unidentified flying objects, find them, and that would include killer asteroids. And I'm doing that with a guy that some of you might know. He's a special effects maven, the guy who, the legend in special effects. His name is Douglas Trumbull. Maybe you heard Doug? Yeah. Well, Doug and I, we met like six and a half years ago now, because I was doing an NPR show, and they said, I got to get you on the show with Doug Trumbull next time. And I went, Doug Trumbull? Childhood idol. The guy was a special effects wizard. I own a visual effects company now, in part because of him. I just took on the same role. I love that stuff. Well, in any case, the guy and I met, and he put me right to work on a Burger King commercial and a few other things, because my site really looks nice with the stuff we've done. And we became very good friends, and we decided to take his system to look for unidentified flying objects. He wants to find these anomalies too. And we kind of miniaturized it to make it, and he called it UFOTOG, U-F-O-T-O-G, because in his day, photographers were called photogs. It was kind of a nickname. So UFO-TOG, it's a little play on the word. Well, we called it UFOTOG 2, right? Numeral 2. And then we changed the name to the Aerial Anomaly Detection System. Sounds really official. But we did that because, like I said, I think if you were there for the tent talk, if you have UFO in the name, say bye-bye to funding. Because we're still fighting a lot of stereotypes, aren't we? We just want to find out if they're here. We want to use science to do it. And if we find it, we have these little platters that are going to have 5 or 6 little units apiece on them that can detect different things: gravitational changes, magnetic changes, infrared, ultraviolet spectra, visible spectra. Okay, changes like that, changes to the electric field nearby. And if any of those things are kicked off when it catches something in the sky, we have another one that's only about a mile away. That these things work in a triad, we call them. And they're kind of, remember the show War of the Worlds? Not that. But In Search of is coming out new now. It used to be an old TV series, and now they're remaking it. And I did the first episode for it in Boston. And then that, there was I think it was War of the Worlds, where the Martian machines landed in these triangular patterns. Well, there's a reason that they did that in a movie, but there's another reason we're actually doing it in real life. Because with these triads, we can link them to each other very easily. So if one sees it, then the second one in the line can see it. And then we can have 2 things that have 5 observations apiece of this object in the sky. And guess what we can do? We can triangulate. We can figure out how high it is, how fast it's moving, all the data. That's incredible, and that's what we're going to try and do. So, yeah.
I don't know if you followed the recent announcement from NASA, but they discovered methane on Mars.
My Sunday night radio show, I'm a KGRA host. I have a show called Sky Tour Radio on KGRA. Sunday night, you want to listen. Because Sunday night, I was going to talk about the planet Jupiter, because we're doing I do an astronomy show on KGRA, which is kgraradio.com. And the show is called Sky Tour Radio, 9 p.m. Eastern Time on Sundays. The reason that we are doing that is because the Curiosity rover at Mars found methane. Methane is produced by volcanoes and microbes, okay? And so it's possible that there's methane on Mars because there's actually life under Mars. Because every summer, this rover on Mars was able to discover that methane was increasing during the Martian summer. Now, that's because we really built these things great. They outlived, their intended usefulness, which was 90 days, by years. And so they ended up staying there to track this methane over and over. And they put the data all together finally, and they see that thank you guys. They put the data together and they found that this thing actually, this planet's actually producing methane in the same way every summer. And that's cool. And on top of that, they found organic compounds. What are organic compounds? Carbon compounds that usually have oxygen and nitrogen and hydrogen bonded into them, okay, from which we are made. So again, remember I talked about the carbon template and we talked about carbon chauvinism? Well, there you go. See, now we see that that's not such a chauvinistic thing after all. Oh, you gotta leave? Okay, see ya.
Should we have Mark back next year? This was.
You know, when you see the National History of New York and you see the timeline in the circle,
That's the Cliff Notes version. This is the real one.
They didn't want my toilet paper.
don't forget Sky Tour live stream as well.
Oh yeah,
on YouTube.
the SkyTour live stream is the companion to SkyTour Radio, so it's all things SkyTour. If you look up SkyTour live stream on YouTube, you'll find me, and you can join us for evenings of stargazing where we actually look at deep sky objects. SkyTour Radio every Sunday at 9 p.m. on kgraradio.com. We have almost 1 million listeners. Be 1,000,001.
We need to take a picture before you leave.
Oh my God. You want to do it
I'll
together?
take
Can you
it.
send
I'll
me
take
the-
it.
Is it okay if
I'll
I
email
put
it
it
to
on
you.
my? Is it okay if I put it on my?
You can do whatever you want.
And how do I
I'll email it to you.
Yeah, and how do I get on YouTube? Like, how do I?
Take that down,
Yeah.
edit it,